We've learned about discrete distributions, and now we're going to move to continuous distributions. Difference between the two really comes down to probabilities. When we work with discrete distributions, we can calculate an exact probability for each outcome because we limit our choices to typically whole numbers. With continuous distributions, we can take any number between our two fixed points all the way out to, let's say, 1,000,000 decimal places. So if we ask the probability of drawing a single number from a continuous distribution, the probability is essentially zero because of all the decimal points that we can use. So how do we calculate probabilities if we have a continuous distribution? In order to calculate probabilities, we have to utilize the actual equations of the densities. The probability distributions themselves are represented by a curve called the probability density function. Our probabilities are going to be represented by the area underneath that curve. So if we ask the probability of a single number, what we're actually going to do is calculate an area under that curve right around that number, because the probability of the number itself is equal to 0. Now, we can take this probability density function and figure out the area under the curve, but others have done that for us and have given us that equation called the cumulative distribution function. So this cumulative distribution function actually gives us that area under the curve. Now, the total area under the curve has to sum to 1 because that is all of our possibilities. We can use the equations to actually calculate this area under the curve, or we can use R. Alternatively, if we don't have the formulas, or if the formulas are too complex, we can go to tables, statistical tables, to obtain our probabilities. Now, before we move on, I do want to make a note of what's in the red box. With a discrete distribution, if we ask the probability of getting a value that's less than some number, that's going to be different than asking the probability of our value being less than or equal to that number. So for example, if we were looking at clutch sizes, maximum of six offspring per clutch, and we want to know the probability of getting less than 2 males in that clutch, that's going to be different than the probability of getting 2 or fewer males. But with a continuous distribution, we don't make that distinction. So if we ask the probability of getting a value less than 10, that's going to be the same as the probability of getting the value less than or equal to 10. And we'll come back and talk about this just a little bit more later in this presentation. So what are the continuous distributions that we may encounter in this class? We can encounter several of them. First one of the ones we'll encounter is a t-distribution. We're going to use this t-distribution to calculate confidence intervals of means and to also perform t-tests. Chi-square distributions are another continuous distribution. We could use those to calculate the confidence interval of variances, which we won't do, and we'll also use the chi-square distribution as part of our chi-square goodness of fit tests or our g-tests. The f-distribution is used when we do the ANOVA. So our test statistic when we perform an analysis of variance should follow an f-distribution. We can also utilize the f-distribution if we compare variances. Finally, we'll also talk about the normal distribution, and the normal distribution is the focus of this presentation. We utilize the normal distribution whenever we perform a one-sample test of means for a population. Note, it's for a population and not for a sample. If we were doing a one-sample test, we'd do a t-test and use the t-distribution. But if we have a population, then we're going to use a normal distribution. So what is the normal distribution? Well, the normal distribution is probably one of the most important distributions that you'll learn. The reason it's most important is because all of our parametric tests assume that the data follow a normal distribution. This will be one of our assumptions of most of the tests that we perform. Now, I have parametric tests in bold, which suggests that this is a key term. Well, a parametric test just basically is a test that assumes normally distributed data. A non-parametric test assumes non-normality. All right, so what are the characteristics of our normal distribution? Well, you're probably familiar with the normal curve because it's the bell curve. It has this shape of a bell. This bell is defined by two terms. It's defined by the mean, which is our central tendency, and it's defined by the standard deviation, or the spread of our data. So we have an infinite number of different normal curves that we could produce, because we can change, or we're free to change, our mean and or our standard deviation. When we say that a population or a data point follows a normal distribution, what we typically say is that data point follows a normal defined by our mu, or standard deviation, sigma. This normal curve can run from negative infinity to positive infinity, so no limits, but in reality we typically only go to 3 standard deviations away. Even at 3 standard deviations, the probability of getting a data point at 3 standard deviations is pretty low. It's about less than 1%. And if we go even farther, it's essentially less than 1% or less than 0.1%, and it's so small that we can pretty much ignore it. So even though the distribution goes from negative infinity to positive infinity, in reality we're normally capped at about 3 standard deviations away. Lastly, this curve is symmetric around the mean, and we've already talked about how a normal distribution has a mean that's equal to the median that has the mode. Well, it means we're symmetric if we're normally distributed, and that means that the area under the curve, let's say to the left of -1, is going to be equal to the area under the curve to the right of 1. So area on one side is the same as the area on the other side, because we're symmetric, because each half is a mirror image. So here are some useful relationships. I'm not going to ask you to memorize it, but in a way you probably will somewhat learn these values. So if we have our mean and we go 1 standard deviation away from the mean, then that region is about 68% of all of our data points. If we go to 2 standard deviations away from the mean, we capture a little bit more than 95% of all of our data points. At 3 standard deviations away, we're over 99.5% of our data points. Now, the decimal points here are a little bit confusing. We normally deal with 50%, 95%, or 99%, so I give you those relationships. If we wanted 50% of our data points, which would be basically our interquartile range, it's our mean plus or minus 0.674 standard deviations away. If we wanted 95% of our data points, or a 95% confidence interval, it is 1.96 standard deviations away. And I'll note that this 1.96 is the exact value. If we wanted 99% of our items, 99% of all of our data points is 2.576 standard deviations away. So as you can say, a 2 standard deviation approximates 95%, but it would be even better just to say 1.96. Now I mentioned the cumulative distribution function. This gives us that area under the curve. This function generates an S-curve, S-shaped curve. So if we take the probabilities going from negative infinity and looking at the cumulative probability, so all of the area to the left of each individual point, we ultimately get to 1, to 100% of our probability, and the shape of that curve is S-shaped. How can we use this information? Well, if this is what a normal curve should be, then what we could do is plot our actual data versus this theoretical data. This generates what we would term a quantile-quantile plot. So these are the quantiles to generate this CDF function. All right, we're basically plotting observed quantiles versus expected quantiles. If our data follows this S-shaped curve, then each of our observed quantiles match the predictive quantiles, which would thus give us a line of slope 1. So all of our points would fall on a line with slope 1. How would we use this then? Well, we can use how well our points fall on this line as an estimate of normality of our data. So if our points actually fall on this line, then we could conclude our variable is normally distributed. If our points are not on this line, so if, let's say, they are curved this way, or if they have some sort of shape to them, then we would conclude that our underlying data do not follow a normal distribution and thus are not normally distributed. Are we going to do it in this presentation? No. This is the focus of our next presentation. So before we start working with the probabilities, we have to introduce this idea of standard deviate. Now in the useful functions slide, I talked about the useful relationship. So 2 standard deviations away from the mean is a little more than 95% of our data points. At the same token, I said 95% of the data points are captured at 1.96 standard deviates away, 1.96 standard deviations away. Well, that standard deviations is a standard deviate. Standard deviate is essentially a conversion of our individual points and reporting them as the number of standard deviation units away from our mean. This is also called a z-score. So you may encounter it online if you search for calculating probabilities using the normal distribution, or if you've had another stats class, you may have been introduced to this idea of a z-score. How do we calculate the z-score? Well, it's pretty easy. We take our value, x, we subtract the population mean, and then we divide by the population standard deviation. So what happens is when we subtract all of our data by the mean of our population, it shifts all of our data so that we are now centered on 0. When we divide by the standard deviation, we now compress or expand our curves so that we have a standard deviation now of 1. So if we apply this equation to each of our data points, then what we do is convert our variable that used to be a normal with a mean of mu and a standard deviation of sigma, we convert it to a z-score, which now has a normal distribution, mean of 0, and standard deviation of 1. Why is this important? This is important because it now allows us to utilize statistical tables to calculate probabilities. All of the tables that we find are reported as a 0-1 distribution. Now, we don't have to do this when we work in R, because R will do the conversion for us. But if we have any probability problems that we have to do by hand, then what we have to first do is calculate the z-score, and then utilize the z-score and look up the probabilities on our table. So why would we calculate probabilities? Well, knowing our underlying distribution and calculating the standard deviates will allow us to answer a couple different questions. One question could be, if we have a population, what's the probability of drawing an individual that is less than some known value, or that's greater than some known value? Or perhaps, what's the probability of drawing an individual that is between 2 fixed values? As long as we know the entire population and that population is normally distributed, we can easily calculate this, calculate the probabilities by hand using statistical tables. We also do a z-score if we have a sample and we have the mean of the sample and we're comparing it to a population. So we can ask, well, what's the probability that our sample mean is greater than some value, or that our sample mean is less than some value? We would calculate a z-score doing pretty much the same way, but now what we've done is compared a sample to the actual population. This is also a z-score test, a z-test. Now, this type of question is a hypothesis testing. So, most likely case would be if you are measuring some unknowns and you say, is this unknown, is this average equal to what's reported for a specific species? So, the question would be, is this unknown our species of interest? Well, we know our species of interest. That represents our population. Our unknown is a sample. we do a z-score, or we calculate the z-score and the probability, and that's our hypothesis testing. So in all cases with these questions, our population, or the sample that we are comparing it to, all must be normally distributed. If they're not, or if we don't know what our population distribution is, then that kind of goes back to our t-test. And we'll make this distinction. So how do we calculate the probabilities? I mentioned we had statistical tables that we can use. And we've got two statistical tables on Blackboard that I've posted. And if you do a search, you'll find many more. The one that I prefer is this one. It's called normal table. The reason I prefer it is because it's two sides. It's 2 pages. So on one page, it gives us the area to the left of our value, and the other page is to the right of our value. So here is the actual table. So on one page, it's to the left of the value. What this is giving us the probability that we would obtain a value that's less than or equal to z, and z's our z-score. So this shaded area tells us the value that all of these numbers follow, or that all of these numbers are giving. On the second page, it gives us the probability that we're going to get a value to the right of our z-score. So you'll notice that all these values are smaller than these. Well, if we add up the values, so take this, the topmost point, 0.5359, and add it to the topmost point here, they will sum to 1, because what we've done is taken the area to the left and the area to the right and added it. Also, you'll notice in the top left, the value is 0.5. Well, our distribution's symmetric. So if we look at the area to the left of 0, we should have half of all of our possibilities there, so 50% chance. Likewise, if we go to the right of 0, then that's 0.5. The other table, the biometry tables, table and normal curve cropped PDF, only gives one side. And this curve gives us the area from 0 up to z. So I'm not going to open it, because I really prefer using this table, and this is the table that I'll use in the examples. But instead of giving the area all the way to the left, what it does is only gives the area from 0 up to z. So if you wanted the area all to the left, what you have to do is take the area that's in the table and then add 0.5 for the other half. It has some use, but I'll show you how to use this table for all of our probabilities. So how do we read our table? Well, the table's set up so that our very first column gives us the most of the numbers that we need, and then all of the rest of the columns are the 0.01 digits. So for this example, 1.75, what we're going to do is read down to the 1.7 row and then across to the 0.05 column. So 1.75, here's our z, 1.7, we're right here, and then we're going to go to the 0.05, so this represents 1.75. So 0.9599. Alright, if we wanted to know 0.63, well, it's 0.6, and then we go to 0.03. So that's our 0.63. And it's the same on this side too. So if we wanted 2.66, we go 2.6, and then we go to the 0.06 across here, and that's our area to the right of 2.66. We'll get some practice. So here's our example. If we know that the wing length of roaches is normally distributed with a mean of 15 and a standard deviation of 2, then what's the probability that we find an individual with a wing length that's less than 18? Alright, so this is written mathematically. This is more of our word problem. What's the probability that any one roach is going to have a wing length that's smaller than 18? It's going to help to do our curve. So our distribution is a normal distribution we are centered at 15. Alright, and we have a standard deviation of 2, and that's what this curve represents. We want to know the probability of finding an individual that's less than 18. So here's 18. We want to know this entire area because that represents the probability that x is less than 18. Now we can do this in R, and I'll show you how to do it in R, but we're going to do this by hand using the table. So what we're going to have to first do is convert this to a z-score. So we take x minus mu divided by sigma. Now where is mu and sigma? It's given in our problem. Mu is 15, that's our population mean. Sigma is 2, that's our standard deviation. So x minus mu over sigma, that goes to a z. Our number, 18, minus 15 over 2 becomes 1.5. So what that says is 18 is 1.5 standard deviation units away from the mean. And now what we're going to do is calculate the probability that we obtain a value that's less than 1.5 standard deviations away. Now this is less than 1.5 above the mean. It includes everything to the left. So what we have to do is take our table. We want to go to 1.50 and we're to the left. So we're going to use this one. We're to the left of our value. We go to 1.5, we're in the correct row, and our hundredths place is 0. So we take that column right there. Our probability that we would find a roach that's less than 18, or with a wing length less than 18 units, is 0.9332, or 93, a little more than 93% chance. So that was the example. Here are 4 practice problems. All of these practice problems, I tell you, data follow a normal distribution, and we will find area under the curve either to the left of a value, to the right of a value, or between 2 values. Remember, it would probably be easiest to draw a curve and then figure out what area we're looking for before you calculate your z-scores. And then once you have your z-scores, utilize the table. So take some time, try to answer each of these questions using the procedure that we did here as a guide. Pause this video, work on it, and then we will go over the answers. So hopefully you've taken some time to calculate these probabilities. Here are my answers. You may have stumbled, been a little bit concerned about about doing the first problem, so let's now walk you through and show you how I actually calculated each of these numbers. So question 1 tells us that the population has a mean of 28, standard deviation of 3.5. And the question is, what's the probability that we would find a worm that's larger than 33? So as I said, it helps if we draw a diagram. Our population is centered at 28. We want to know the probability of finding an individual that's greater than 33, so we are looking for the area under the curve to the right of 33. Now, we know the population is normally distributed, so what we can do is convert to a z-score. We subtract our mean, divide by the standard deviation in order to get these z-scores. So when I do this calculation, I get the probability that z is greater than 1.43. I then go to the table, go to 1.4 and across to the 0.03 column to find our probability of 0.0764. Now, does this make sense? And this is something you should always ask yourself. Does this value, 0.0764, does that make sense? Well, we're less than half of our area under the curve, so we know that it can't be more than 0.5. 33 is more than 3.5 standard deviation units away, and we said that 1 standard deviation units away is a little bit more than 68% of our data points, So 68 divided by 2 is 34. So if you took 0.5 minus 0.34, that kind of gives you an idea of the area to the right of 1 standard deviation. Well, we're beyond that, so our frequency is much lower. So yes, does this make sense? It does. Probability of 0.0764 or 7.64%. Now, you see how I do this one. Now, if you need a little bit more time, please pause this video and try to do question number 2. Question number 2 tells us that the population has a mean of 21.7, standard deviation of 10.2, and we want to know what's the probability that we'd get a value that's less than 9. So again, it helps to draw a diagram. So our normal curve is centered at 21.7. We are interested in finding the area under the curve to the right of 9. So again, our population is normally distributed, so we should convert to a z-score using the mean and the standard deviation of our population. And when we do this, I get a z that's less than negative 1.25. Now, our table doesn't have negatives in it. Our table is all positive. But that's okay, because if we look at these distributions, we would realize that our area under the curve of a normal curve are symmetric around that mean. So we are looking for the area to the left of this negative 1.25. Well, that is the same as if we were looking for the area to the right of positive 1.25. Why are the areas the same? It's because our normal curve is symmetric around our mean. And this mean was 0 since these are the z-scores. So we have probability that z is less than negative 1.25. Well, that's going to be the same as calculating the probability that z is greater than a positive 1.25. We have that in our table. Using our table, we can calculate the probability as 0.1056. Question 3 tells us that the population has a mean of 1.78 and a standard deviation of 0.6. Unlike the previous two problems, this question is asking what's the probability of having a number that's between two other numbers. So I'm going to do it using figures. So we have our population. It's centered at 1.78. We want to know the probability of finding a value that's between 1 and 2. So we are looking for this area. One way that we can do it is break it up into two different areas. So we can first take that 1.78 and calculate the area to the left of 2. So calculate this entire area. Then what we can do is subtract out the area that we don't want to use. So the area that we don't want is all of that area to the left of 1. So if we subtract out those areas, we'll get our area of interest. So we would get this area. So calculate the larger, subtract out the smaller, and we get the area. Now, I can do it all as one big inequality, but for this one, I will do it individually. So we are asking for the probability that x is less than 2. We're normally distributed, so we will calculate the z-scores. So 2 minus the mean divided by the standard deviation. And this gives us the probability that z is going to be less than 0.37. We can then use our table to calculate that probability, which is 0.6443. Now that's all of the area to the left of 2. We also need to find the area to the left of 1, because we will have to subtract it out. Now, just like before, what we are going to do is convert it to a z-score. Oh, it's not 0.68, 0.6. Get this corrected. So we have probability that z is less than negative 1.30. Well, just like question number 2, this is the same as the probability that z is greater than a positive 1.30. So using the page 2 of the table, we can see that this probability is 0.0968. Now, those are the individual probabilities. We still have to get our total, so we would subtract them. So 0.6443 minus 0.0968, and that gives us a total probability of 0.5475. So I will point out that this is probability that we have negative 1.30 is less than z is less than 0.37. So as I said, we could do it with one large probability, one large inequality, or we can split it up into individual parts. Question 4 tells us that our population has a population mean of 70, standard deviation of 3. In this question, we want to know the probability of finding an individual that's between 65 and 68. So, if this is our population, we are centered at 70. We want to know that proportion that is between 65 and 68. So we are looking for that area. Now, just like before, what we can do is separate it into different portions. So we are looking for the area to the left of 68. So this entire area, including the tail, and then we can subtract out all of the area to the left of 65. And that leaves us with the area of interest. And to do this, we would have to calculate our z-score. So, doing it as a large inequality, what I can do is convert all of this to a z-score. So, subtract our mean, divide by our standard deviation. And what we get is the probability that our z is between our two values. And the two values is negative 1.67 and negative 0.67. Now this is the same as asking the probability that our positive 1.67 is greater than z is greater than positive 0.67. So again, it's mirror image, so I just flip it, and when I flip it to positives, I switch my less than to greater than signs. So we've got area that's to the right of 0.67 minus the area to the left of 0.67. So z is greater than 0.67 minus that area to the right of positive 1.67. So it's the larger area minus the smaller area gives us our area of interest. So I get 0.2514 for the larger area, I get 0.0475 for the smallest area, and that means our overall probability of drawing an individual between 65 and 68 is 0.2039. So we calculated these problems, or the probabilities, by hand using statistical tables. Can we do this in R? Yes, we we can do it in R, and it's really easy. The function that we'll use is p-norm. So p is our percentile, or I don't want to say probability, but it's a percentile. It's going to give us the area to the under the curve to the left of some value, and we're going to use the normal distribution as our distribution of interest. What we're interested in is the probability that we get a value less than or equal to x if our population has a mean and a standard deviation. This lower dot tail is interesting because this tells us the area to the left versus the area to the right of our point x. So if we looked at our distribution, the help file of that distribution, it gives us a little bit more information. So we had d norm, or we've had d binom and d poise, but we talked about d, that's our density. That's basically the height of the curve, of the PDF curve, but it doesn't give us a probability. R is the random. We generated a random number. We're going to use p. Now if we look at the lower dot tail option, it gives us this. So it's going to be illogical. We're going to use lower dot tail equals t or lower dot tail equals f. If lower dot tail is equal to true, or capital T, then we're looking for the probability that x is less than or equal to the value that we give it. If we set lower dot tail equals false, it's going to give us probability that x is greater than the value. So note, this is the lower dot tail equals t is less than or equal to. The lower dot tail equals false is greater than. Now, does this matter for continuous distributions? Not at all. As I said, this x is less than or equal to x is the same as big X is less than x for a continuous distribution. This will be important if we utilize, or if we're calculating probabilities by hand of binomial or Poisson distributions. Then we have to be aware of if we're including the value or if we're not including the value. So the p-binom function is pretty easy to do. Let's do an example. If the wing length of roaches is normally distributed with a mean of 15 and a standard deviation of 2, then what's the probability that we find an individual less than 18? We did this probability by hand, and we came up with a probability of 0.933. What does R give us? Well, for R, we don't have to calculate a z-score. All that we have to do is tell it the value that we're asking, 18, so that's up here. We tell it the population mean and standard deviation, and then we specify lower dot tail. So since we're going less than 18, we want the area under the curve to the left of that value, 18. So we use lower dot tail equals t, and we get this value, 0.9331928. Real easy. So we're going to go back to these practice problems. We did all of these probabilities by hand. Now go ahead and use R to calculate the probabilities. Remember, we don't have to calculate z-scores. R will do it for us. We just have to give it the value, our x value, give it our mean and standard deviation, and then determine if we're doing the lower dot tail equals t, which is to the left of our value, or lower dot tail equals f to the right of the value. So hit pause, pull out, open up RStudio, try to calculate these probabilities. So hopefully you had a pretty easy time calculating these probabilities. Let's work through it. So in my R Markdown document, I went ahead and gave it functions, kind of described what we are calculating for using this p-norm. And I do this just so I have a record, especially useful on a quiz or a test. So first practice problem told us the normal distribution is 28, standard deviation 3.5. What's the probability that an individual is greater than 33? So this is a p-norm. Our target value is 33. The mean of our population is 28. Standard deviation is 3.5, and lower dot tail is false. We are going to the right because we said x is greater than 33. When I run it, I get 0.07656. I'll note this number may be slightly different than how we did it by hand. It's because r did not round. We round when we do it by hand. R doesn't round, then R can calculate an exact probability. So some of our values in R may be slightly different than if we do it by hand. Question 2 has a population with a mean of 21.7, standard deviation of 10.2, and we ask what's the probability that our value is less than 9. If you remember in this one, we had a negative value when we converted to a z-score, so then we had to convert it to a positive and so forth. Not here. All we have to do is give it our value, so p norm of 9, give it our mean and standard deviation, and tell it lower.tail equals t because it's to the left. R will handle all of the conversions to z-scores and handle all of the negatives and positives. So we get our answer, 0.1065. Now this one is different. Remember, we had 1056. This one's a little bit different. Again, it's because of rounding. Question 3 gave us a normal distribution with a mean of 1.78, standard deviation of 0.6. We wanted to know the probability that we get a value between 1 and 2. This is real easy. We don't really have to draw a diagram. You can, but I say these are easy because what I suggest doing is taking the larger value and always subtracting the smaller value. So we have p norm of 2, mean of 1.78, SD of 0.6, lower.tail equals t. All right, so I take the larger value, we're to the left of it, so lower.tail equals t. I'm going to copy this, paste it, and change 2 to 1. So we took the larger value, the area to the left of the larger value, subtracted the area to the left of the smaller value, and I get 0.546267. Again, any difference between this number and the one we get by hand is entirely due to rounding. So question 4, normal distribution with a mean of 70, standard deviation of 3. What's the probability that we get a value between 65 and 68? It's going to be the exact same thing. I'm going to use lower.tail equals t. I'm going to take the larger value and subtract the smaller value, t. I'm going to subtract my smaller value of 65, calculate it, and I get 0.2047. So again, it's very easy to do it in R. If you have the between values, then I always suggest taking the larger value, subtracting the smaller value. You can diagram it on a piece of scratch paper to help you conceptualize that area that you're calculating. But in R, since R handles all of the z-scores for us and handles the positives and negatives, just use p norm, give it the x value, and specify our distribution. So these are calculating our probabilities, and these are calculating probabilities less than a value and so forth. And you might wonder, how is this applicable to statistics? As I said, we can do hypothesis testing, and we can say we have a sample mean and we're comparing it to a known population. Well, that's a hypothesis test, and calculating the probability of finding a value, a sample mean, gives us a p-value, which is the probability of getting that value or a value that's more extreme. So that is the area under the curve, either to the right of our value, so greater than our value, or to the left of our value. So, and we'll do this once we introduce hypothesis testing. But for now, if we're going to calculate these probabilities, here are my recommendations for doing it. And this is especially true if you're doing it by hand. So first up, draw a rough sketch of that normal curve. Label your mean, figure out what area we're trying to calculate. So look at the area under the curve. That'll help you keep track of the greater than or less than areas. Also, note which areas you may have to subtract out if we're looking for probabilities between two values. Once you know what areas you're going to calculate, then go ahead and convert your values to a z-score. And then once you have a z-score, then utilize your probability table to find the actual probability. If we're in R, we don't have to do the z-scores. You know what areas we're going to calculate, just use the p-norm function to calculate those probabilities. Now, these are all normal distributions, or data that follows a normal distribution. Sometimes we don't follow a normal distribution. If we don't follow a normal distribution, then what does the curve look like? Well, non-normal data could be skewed and or peaked. So skewness refers to the asymmetry of our distribution. So normal curve is symmetric, where our mean is equal to the median, which is equal to the mode. If we are skewed right, then we have a long tail towards the right-hand side. That's going to bring the mean higher than the median, which is higher than the mode. If we are skewed left, then we have a long tail towards the left of our peak. So it brings the median lower to the left. The mean is to the left of the median, which is to the left of the mode. Now, if the tail's keeping track of a right skew as a long tail on the right, or a left skew as long tail to the left, if that's hard for you to remember, I've always remembered it as saying, if we skew right, then our distribution is leaning to the left. If we're skewed left, we're leaning to the right. Kurtosis tells us the peakedness or the shoulderedness of our data. So what we're looking at is not so much are we asymmetric, but now do most of the points fall around our mean, and in which case we're peaked or leptokurtic. Or are most of our points kind of flattened and spread out through the middle portion of our distribution? This would be platykurtic. Now it's not just peaked or shouldered, but our peak, if we're leptokurtic and we have more in the peak, it's more in the peak and more in the tails out here. So this pink line actually is above the black line in our extreme values. So we're more in the peak, more in the tails, which means we are less in our shoulder region here. If we're platykurtic, we're flattened. And that means we have fewer points in our peak, fewer points in our tail way out in this region, but have more points in our actual shoulder of the curve. Can we test these? Yeah, we can test these. We can run a statistical test that checks for asymmetry and kurtosis, or we can run an assessment where we kind of look at some graphs and see if the graphs appear to be asymmetric or peaked or shoulderedness. I'll note bimodal distributions. Those are considered extremely platykurtic because we've got a huge number of points in our shoulders and not much around the mean or in our tails. So that ends our introduction to normal distributions. We are now going to be moving towards doing this assessment of normal data. Why? It's because our hypothesis tests that we introduce all assume that our data are normally distributed. And before we can perform our test, we have to check that assumption. So we will now move to the next presentation of assessing normality.